Hello everybody, my name is Chen Liu. I'm a PhD student at UCL. I'm going to introduce you our work, Neural Differential Appearance Equations, jointly done by me and my supervisor Tobias Ritual. Our work is about generative AI for dynamic appearance. One example of dynamic appearance is the rusting process. Like, this is a video of a piece of metal that's getting rusty. We generate new instances of the same rusting process given this video. Furthermore, if the input video is under the calibrated lighting, like this center flash light, we can generate temporally and spatially varying BIDF maps using differential renderer, which can be rendered with novel lightings like this. Before, the standard way to authoring such a set is procedural texture, which requires expertise, manual label, and time to create just one. In this work, we show that with our method, you don't need any of them. Instead, you can use your cell phone to capture and use our method to generate whatever dynamic appearance you can capture. This is an example we capture. Some clay is drying. So how do we achieve this? Let's start from the simpler case where we want to generate some dynamic textures. We ask a primary question: what brings the left to the right? There are two frames from the rusting video you saw. You can imagine there is a process describing the interplay between the metal, air, oxygen, water, which eventually produces the rust. So what is it? In fact, it is highly relevant to differential equations. Back in time, a seminal work done by Turing claims that there are many biological equations which can explain texture patterns found in animals, like zebra stripes. This idea is then adopted by Whittaker and Cass, who handcrafted some equations for texture synthesis. It allows you to solve an equation to get static textures from noises. A recent work called DYNCA incorporates machine learning, which learns motion equations from data. So the rusting process might be a chemical process governed by a differential equation. We just cannot easily write it down, so we propose to use neural differential equations to learn it. Specifically, while using neural ordinary differential equations, ODEs represented by neural networks. Let's look at our approach. Our approach basically learns a neural ODE for appearance change from the example video. The first thing is of course the data. We show a sequence of images from the rusting process. They are in RGB space. They start at TS and end at TE. We use the symbol L hat for it. Our goal is to generate LT, which is a stochastic realization of this rusting process. Neural ODE is a way of modeling time-varying signal. For example, say here we have a state ZT which has the blue trajectory. We model its dynamics, the trajectory, using neural ODE. As seen in these orange arrows, the gradient of z with respect to time is a function f, parameterized by theta, a neural network, which takes the current z and time as input and outputs the gradient, the update. Then we can solve the trajectory to any time by some off-the-shelf ODE solver. We further define our state in a latent space. So it is no longer RGB, it is a latent distribution we don't know. Our latent space is not pre-trained but jointly trained with the entire model. We then project those latents back to RGB. The latent state is projected by a function rho. The latent space we use here is channel augmentation inspired by augmented ODEs. Specifically, our latent states have 12 channels, and the projection rho simply extracts the first 3 channels to be the RGB image. It is simple, but it significantly improves the result. Since we are generating models, we start from noises. The time range is split into 2 phases. One is the generation phase, we saw before, where we deploy the solution of our neural ODE as a generated dynamic texture. Another one is warm-up, which is earlier than the generation. At the phase, ODE start from random Gaussian noises and gradually drive the noises to valid appearances in the first frame at TS. This phase is reminiscent of the diffusion model that we start from noise, then gradually denoise it into an image. But our method is different from that because we care beyond the first frame. We train ODEs to solve an entire trajectory to get subsequent appearance evolution. Last, to compute the loss, we minimize the VGG textural loss, slice versatile loss, which is arguably SOTA textural loss, between one frame in the bottom and the corresponding target frame at the same time point. It is done for the entire generation phase. Next, we show our result. This is what you saw before, the metal rusting. Left is the input, right is ours. The output is larger than the input because we start from a larger noise, a common practice in texture synthesis to show the diversity of the method. This is growing, some seeds are sprouting. And this is honeycomb melting. Okay, so far we show our method can generate dynamic textures, but still one problem. Textures are not relatable. We want to model the essence of the time-varying materials, so we model dynamic BRDF maps. We first capture some dataset. Our physical capture setup is basically the same as the one used in Itala's talk paper in 2015. This is the schema and the photo of our setup. We use a smartphone with camera and flashlight close enough to each other. We take photos with flashlight which is strong enough to be the dominant lighting. This calibrated illumination enables inverse rendering to reconstruct SVBRDF maps from fresh images. Additionally, we use a tripod to capture fresh time-lapse videos for many dynamic appearance phenomena. This is an example data we captured. It is a piece of copper that is patinating. Here are more previews from our dataset. We show two examples of drying and melting respectively. Some of them has been commonly used and researched in production, like clay. We further model its drying process. Some of them is a bit exotic, like food appearance, such as cheese and honeycomb. This could also be a serious topic because they happen almost every day in our daily life, while remaining rather unexplored. And besides data capture, we couple our pipeline with a differential renderer, which is basically a digital replica of the physical setup. We use anisotropic Cook-Torrance BRDF model, which has 9 parameters. Therefore, our SV BRDF maps have 9 channels in total. So what changes in our pipeline? We still have data, and we still model neural OD in latent space. The difference is here. When we project our latents to RGBs, we now extract the first 9 channels to be the SVBRDF maps. And then we render them to final RGB pixels using the differential renderer, and then compute the loss. We use a variant of slice versatile loss for our SVBRDF case. You can see the details in the paper. So let me show some results. Here the leftmost is the input. This is a synthetic rusting data we create in Blender. The middle column is the dynamic SVBRDF maps we generate. It has a few insets representing the diffuse, specular to roughness maps and normal map. On the right is the rendering with novel lighting conditions. The dynamic BRDF maps well explain the rusting process. The roughness increases over time, and in the normal map, these rough bumps are gradually forming, just like real rust. And the final rendering looks realistic. This is another result. Some clay is drying. Look at our rendering. The drying process has been well generated. You can feel it is wet at first, but the clay gradually becomes drier and drier, and the highlights are becoming more and more diffuse over time. We show the final one, cheese melting. For this one, I want to point you to the normal map. You can see the cheese stripes in the beginning, and those stripes are gradually forming some bubble dots and become very rough eventually. To conclude, we propose new differential appearance equations for dynamic appearance. We capture and release a pilot time-varying appearance dataset. One take-home message: neural differential equation is a good representation of dynamics. And here we show some metadata of our project. There's a QR code to our project page where you can find an interactive result gallery. So please don't forget to check it out. And please feel free to reach out to me if you have any questions or want to talk about my research. Thank you very much.